microphone on the Elmo. All right, can you guys hear me on Zoom now? Awesome, thanks. Yeah, if you guys can't hear me yet, you definitely let me know. So thanks for that. And so I'll repeat a bit of what I said just now. So I know there's been some questions on problem 3 on the homework, and so I'm going to do just a couple quick examples at the beginning today. And I will be unavailable this weekend for answering emails. So I'm leaving actually tomorrow morning. So I'm going to a wedding, my best bud's wedding actually from high school. I expect that I'll be drinking a lot, and so I'll probably be very hungover on Monday, if not dead. And so, you know, and silly me, I scheduled office hours at 9 a.m. on Monday. So, you know, that's my own fault. I kind of forgot that this happened. Okay, and so you know, besides problem 3 on the homework, are there any questions I can answer before we get started today? Okay, right. So let's do a couple more examples of non-standard cash flow conversions. Okay. And so I think there are a couple reasons why these problems are very kind of tricky for a lot of people. I think the first reason is that, you know, you have to make multiple conversions on these. So you can't just look up just one conversion factor in the compound interest table. You have to kind of do this multiple times, and deciding which combination of conversions to pick, I think, can be tricky. But I think also what makes these difficult, particularly the homework problems, that there's just so many things going on, and so, you know, it's hard to kind of know, how to pick out these different cash flows and how to classify them. And so, you know, and so let me I'm going to go over, you know, basically the first case, and so, you know, how we can, you know, do these multiple conversions. And then for the second part, you know, with regards to, you know, lots of things going on, you know, unfortunately with that one, it's best to kind of just have to probably read the problem kind of more than once, draw the cash flow diagrams, because that's kind of really the only way to kind of organize those things. Okay. All right, so let's do a couple of examples. And I'll do this from the cash flow diagrams perspective, because I think that's kind of the easiest way to visualize it. And so I think one cash flow pattern for sure that shows up in the homeworks is when you have a uniform series that is not aligned to the time period of your cash flow diagram, right? Because remember, the kind of the standard form from a uniform series is that it goes for the entire period, right? And so it starts on time period 1. And so in this case, we have 5 time points. And so the standard form for a uniform series would be if we had cash flows on all periods. Okay? So, but oftentimes we don't have this, and so, you know, we might have something like this. Okay. Or say, you know, we only have I'll do one more. And so we only have a uniform series that may extend for just the first 3 years, and then, you know, but then we have some empty spots later on in the cash flow diagram. Okay. And so let's say for this example, let's convert this. Let's convert this to a single lump sum at the end of year 5. Okay. And so, because normally, you know, the way that we do this, and so let me give this a value. And so let's say that this has a value of A, okay? And so if we were to convert this into a single lump sum in year 5, which I'll call F5, you know, we would just do one conversion. So we say A, F over A. We'll say this is interest rate of 6% and 5, right? That's how we would normally do like a standard conversion. But that would only be valid if we had this uniform series extend all the way to year 5, right? And so we can't just do this all in one step, just like that. Okay. And so we have to do this in 2 steps. Okay. All right. And so one way that I like to tackle these problems is that whenever you have any kind of recurring cash flow series, so either that's a uniform series or a gradient, what I like to do is I like to kind of combine this all into one lump sum. Okay. because from that lump sum, it's a lot easier to convert that to, you know, whatever other places that you want. Okay? Okay. All right. And so kind of the actually, you know, when I first draw this, the natural thing that I was thinking is that, you know, to take this, because we have three uniform series, and then convert that into a P. Okay. And so that would be step one. And so step one would be to convert this recurring uniform series into a present day sum. And then from the present day sum, we can then convert that into a single lump sum in year 5. Okay. So that was kind of the first thing that I was thinking about. Let me do it in a little bit of a non-standard way, just so you can kind of get a different look. Okay. And so first thing I'm going to do actually is I'm going to take this and convert it into a future sum, but on year 3. Okay. Okay. And so to do that, so we'll call this F3. Okay. And so F3 will be F over A, 6, what did I say, 6%? Interest rate doesn't matter. We're not actually computing anything. And 3, okay? And so for these non-standard conversions, you know, what I recommend too is to draw all the intermediate cash flow diagrams so that you can see the conversions taking place. Okay. Right. So after we do this one conversion, now our cash flow diagram looks like the following. Okay. And so we took this uniform series and then we lumped it together into a lump sum on year 3. Okay, so this right here will be F3, where F3 is given, the value of F3 is given by that formula up there. Okay. Okay. And so now that we have it in a lump sum on year 3, we can easily convert this into one lump sum on year 5. Okay. And so this is the kind of reason, this is the reason why I kind of did this. And so, you know, you might think that this F3 here, you know, this is some future sum, right? Because it's not on year 0. But, you know, if you look at the conversion that we're doing, we're taking one lump sum in the past and then moving it forward into the future like that. Okay. And so what we do from here is that we say that in this case, since we're moving a single lump sum forward, this F3 is basically going to count as a present sum. Okay. All right, and so we say that F5, which is the one that we want in the end, will be F3. Okay. And the conversion factor that we want is F over P in this case. Okay. And the end value that we choose, we're just moving 2 years into the future. And so we have 2, just like that. Okay. And so we can draw the cash flow diagram one more time. And so after we do that conversion there, then we have this, you know, this cash flow, which is what we wanted in the end. All right, and so now that we've gotten the cash flow diagram for this cash flow, you know, into the form that we need to, we can combine all the steps that we need. All right, and so F5 is equal to F3 times F over P 6% 2, but we know F3 is equal to this right here, okay? And so this is going to be A, F over A, 6% 3, okay? And the second conversion that we did was this one right here. And so then we multiply by F over P, 6% and 2. Okay. And so that's how we would take that uniform series that only extends up to the first 3 years and then transform it into a single lump sum F5. This is one way to do it. So there's other ways, there's other paths that you can take too. But you know, this, I wanted to show this one because I think this one will be a little bit more useful for the homework. All right. And so I know the problem that I think trips people up a lot in the homework is the saving for college problem. And so for that problem, you know, first of all, there's a lot going on in that problem. Okay. Right. And so, you know, let's assume that there's, you know, lots of stuff going on here. Right. And what we say is that when the child is, you know, 18, 19, 21, 20, 21 years old, then we have to pay tuition for those 4 years, right? And so this is a good example of a uniform series that's not standard because it only occurs at the end. Okay? And then, you know, you have to kind of convert this non-uniform series. Okay? Another thing that might be useful for this problem is that, you know, a lot of times, you know, you're solving for the value of a cash flow of something in the middle here, right? And so if you kind of, you know, you read the problem, you write down all the cash flows that are given to you in the problem, you draw the cash flow diagram, you know, oftentimes you're missing some piece of information here, right? And so, for instance, you know, we might be missing, you know, maybe a gradient value here, okay? And so there might be an amount that we, you know, that's not known. Okay? And so in these cases, you know, the best way to tackle these problems is to solve it, you know, kind of like an algebra problem, right? And so you have one unknown. Okay? And so in these situations, you want to set up an algebraic equation to solve for that unknown. And a simple way to set this up is to set up an equality relationship, okay? Where on one side of the equal sign, you have all of the costs associated with the cash flow diagram. Okay. And on the other side, you have all the benefits. Okay. Okay. Where the only way that you can set up this equal sign is if all of these costs and benefits are converted into the same cash flow form. Okay. Okay. And so maybe they're all converted to a present sum. And so I think that's the easiest thing to do. And so to use present worth analysis here, so you convert all the cash flows, even all the non-standard ones, into a P, right? And so if you do that, then you can set up this equality relationship and then just solve for the. And so I think, you know, if I remember correctly, there's 3 parts of problem 3, right? So there's the I think there's a crane problem, there's a college tuition one, and then there's the one where I just show you the cash flow diagram. And so actually the best, I think, in terms of difficulty, the third part C, is actually the easiest. And so if you haven't done that one yet, I would recommend starting with that one, because then that's, I think, kind of a more simple case of this, where you can set up an equation like this, solve for the unknown, and then the other ones kind of follow suit from that. And so if you're kind of still struggling with problem 3, start with part C, and then you can do the other 2 from there. Okay. And of course, if you're still struggling with this, feel free to send me an email. So I'll be here a little bit late today, because I want to finish up some work before I head out tomorrow. And I'll try to answer your email before I head out. Okay, and so any questions on any of this? Yeah. It's not available. Yeah. So if you're converting between F and G, that by itself is a non-standard one. So you have to convert first to like a P, and then there you can convert it to an F. Yeah. All right. So hopefully that's helpful for the homework. All right, so let's go ahead and pick up where we left off on Tuesday. And on Tuesday, we were talking about annual cash flow analysis. All right. And so if you remember, the idea with annual cash flow analysis is that it's kind of another form to do economic comparisons. But instead of converting everything to a present sum of P, we're instead converting all the cash flows into a uniform series. Okay? Okay. And so the idea is that, a lot of times when you're managing an engineering project, or even, just making economic decisions in general, you have several different options that you can consider. And so the idea is to take all the cost, all the revenue, all the benefits, everything for a particular option, convert it into a uniform series, and then compare that number to the uniform series associated with the other alternatives, so that you can choose the one that's most economically efficient. Assuming everything else is equal, of course. So assuming that all the performance and stuff is the same. Okay. And one big advantage that we saw on Tuesday with annual cash flow is that you can compare options with different product lives, or different amounts of life much easier than present. Okay. And so we did an example last time where I think we compared options with like 4 and 8, on lives of 4 and 8, something like that. Okay. And we saw that we didn't have to do anything special in order to get the right answer to it. And so let's take this to kind of the extreme. And so let's consider a case where we have a product life which is basically infinite. Because there are some situations where a project is expected to last for infinity amount of time. Okay. Maybe with minor maintenance here and there, but there are some things that are just expected to last a lifetime. All things considered. And so, a lot of public works projects kind of fall into this category where, we might build a road, we might build a freeway, and then, we only may have to service it very lightly over many years. Okay, and so let's consider 2 options. And so let's consider an expansion to some of the roadways through, or excuse me, let's consider an expansion to some of the piping in LA County. And so there's two options being considered for this expansion. And so one option is to make a tunnel through one of the local mountains. And another option is to make a pipe and have that pipe go around the mountains. Okay. All right, so both are going to have initial costs. They've also been rated for their maintenance. Okay. Okay. And we also have information on their useful lives. Okay. And so for the tunnel through the mountains, it's going to cost $5.5 million. Whereas the pipe going around the mountains, this is going to cost $5 million. Okay, so it's about $500,000 cheaper. We're going to assume that there's no maintenance required, or virtually no maintenance. And so especially compared to the initial cost, we'll assume that maintenance are zero. Okay. And then we have the useful life. And so for the tunnel through the mountains, for all intents and purposes, we don't ever have to replace it, because kind of once you blow a hole through the mountains, then assuming that there's no rock sides or anything, it's going to be there forever. Okay? And so there's basically an infinite useful life there. Whereas the pipe, the pipe is expected to rust, is expected to require replacement, and so we're going to expect to replace this about every 50 years. Okay. All right. And so we're going to assume an interest rate of 6%. And so based on that interest rate and based on these alternatives, we should compute which one should we choose. All right. And so if you take a step back from this problem, or maybe you don't have to, you don't even have to take a step back. You might think that it's obvious, we should pick the one that's permanent, because we pay a little bit more, but then we just don't have to worry about it ever. And then the other one we have to replace it every 50 years. Okay. But what makes this problem complicated is that the $500,000 that you save by going with the pipe what we can do is we can take that $500,000 and invest it in the market, right? Remember, that's kind of the assumption we're always rolling with these comparisons, is that any money saved on initial cost, we invest it in the market at a 6% interest rate. Okay. And so the question that we're really asking ourselves is that $500,000 that we save, is that going to grow enough over the 50 years to make that worth it? Okay. And so the only way we can do that is with annual cash flow analysis. And so actually let's do the pipe around the mountain. So this one is relatively easy to do. Okay. And so we're going to compute the EUAW of the pipe, where we convert this cost to a uniform series. And so our initial cost here is $5 million. And so we're going to have a minus 5 million. And since that is the initial cost, that counts as a P. And so we need to convert this to an A. right? We convert it to a uniform series. And so the conversion factor that we want is A over P. Our interest rate is 6%. And the time period is 50. Okay. And so the EUAW for the pipe is a minus $317,000. Okay. All right, so let's go for the tunnel now. And so for the tunnel, we can do the same thing. Okay, so we have a minus 5.5 million, and so that's 5500000. Okay, we want to take that initial cost and we want to convert it to a uniform series. Our interest rate is 6%. And our end value here is infinity. Okay, because we're assuming, for all intents and purposes, that this tunnel is going to be permanent. And so we're basically spreading that cost over an infinite amount of time. Okay. All right. And so obviously, we can't actually compute this. And so, if probably you guys have looked at the compound interest table a lot, but there's no line for infinity. And so we can't actually compute this. And so the question is, if we have an infinite useful life, how do we compute the EUAW, or what's our option? Well, one option that we have is to use our concept of capitalized cost. So remember, capitalized cost, that was the first thing that we talked about on Tuesday. And so the idea with the capitalized cost is that you invest a very large amount of money at one time, and then you just withdraw the interest on that account for all eternity. Okay. And so it kind of serves as a way where you can take something with an infinite life and then convert that to a uniform series, just based purely on the interest. Okay. All right. And so if you recall, our formula for capitalized cost was that we have A, which is the uniform series amount, is equal to the present sum multiplied by the interest. Right? Because based on the interest rate, each year we can withdraw from the capitalized costs as just the product between the original principal and the interest rate. Okay. And so we can do the same thing here. And so here our P is 5.5 million. And so we have 5500000. Okay. That's our P. Our interest rate here was 6%. And so that's going to be 0.06. Okay. And that's going to equal to our A. But in this case, our A represents the EUAW of the tunnel. All right, so let's go ahead and compute that. And so we have minus 5.5 million multiplied by 0.06. And what we get is minus 330,000. All right. And so our first EUAW is minus 317,000, and the other one is minus 330,000. And so based on this analysis, the better option to do would actually be to build a pipeline going around the mountains. Okay. And so that's not, I think, I like this problem because I think it's not the obvious solution when you're kind of looking at this, having someone explain this to you. Right? But, I think one thing you can never underestimate in economics is you can never underestimate the power of having cash on hand. And so with what may seem like an insignificant amount, if you give that money time to grow, then it can really, make it work. All right, any questions on this example here? Okay. All right. So that's what you would do if you have an infinite life. Okay. Let's talk about some cases when you have an early salvage value. So these are cases when you have some other analysis period. So oftentimes, when you're planning out, the finances or the budget for a long-term engineering project, a lot of times you're only going to use a product, or you're only going to use a machine for a certain amount of time that is less than its useful life. Okay. And so say, you bought a machine and it's rated to last for 12 years, but the project you're working on is only going to last 8. And so at the end of those 8 years, you're going to sell the machine, or you're going to salvage it early. Okay. And so what this leads to is that, you can salvage the parts early, and that's often going to give you more money than if you kind of ran the machine all the way up until its end of life. Okay. All right. And so, we touched on this a little bit in present worth analysis. I know that we didn't have a chance to do an example with it, but I wanted to make sure I cover it here, just that you can kind of see a good example of it. Okay. Because in these situations, the salvage value that you're going to end up using is probably going to be an estimate of its salvage of its value compared to its end of life. Which can be hard to do. And so, I know for sure in homework, not homework 2, but in homework 3, I do give you a problem where, you have to salvage some of the machine early. Okay. And so in those cases, I'm going to give you what the early salvage value is. But sometimes, you just don't know, what that's going to be, because the market might shift over that time and you might not know, how much you can get. Okay. Okay, and so in these situations where you kind of have more unknowns in the problem than you can deal with, kind of the best thing that you can do is to just use your economic analysis technique to set up an equation, and then once you know the numbers, you can kind of just plug it in. All right, so let's do an example of how this is. Okay, so this example has no numbers, and so we're going to use variables to represent everything. But the idea is that if you set up the equation, Then later on, once you know the numbers for like, what the initial cost is, what the early salvage value is, what the late salvage value is, you can just plug those in as you. All right, so let's consider two alternatives. And these alternatives are for a production machine. So this is for some, manufacturing or some company that produces some kind of product. Okay. All right, so we have two alternatives, and so we'll call it machine A. So let's say machine A has a useful life of 7 years. Its initial cost, we don't know what it is, but we can give it a symbol. Okay. And so I'll give that symbol P sub A. And it also has an end of life salvage value, which we'll call F sub A. All right, so now we have machine B. And so machine B will have a useful life of 13 years. Right, the initial cost for option B will be P sub B, which again, we don't know. And we'll assume it has an end of life salvage value of F sub B. Okay. So not all that different from the problems we've looked at, it's just that now everything is in symbols. Okay. All right. And so let's say that for this production machine, the company only plans on using them for 10 years. Okay. And the interest rate here is 8%. All right. And so what we want to do in this problem is we want to set up the equations to compute EUAW for each of these alternatives. All right, so let's go ahead and draw the cash flow diagrams for both of these cases. Okay. All right, so let's do option A first. All right, so we have a useful life of 10 years. And so we know that initially we have to make our initial purchase. And so this is going to be P sub A right here. Okay. And then machine A is going to last 7 years. And so in year 7, we're going to salvage the first machine. And so call this F sub A. But to make sure that we reach all the way to the end of year 10, we're going to purchase another machine in year 7, which we'll call P sub A. All right, and so the second machine, we're going to use it for 3 more years. And then we're going to salvage it at the end of year 10, because that's when the project is expected to conclude. Right? And so here we're salvaging early. And so this is not going to be F sub A, but we're going to create a new variable, which I call F3A, where this F3A is the early salvage value. After 3 years of use. Okay, which we don't know yet, but we can set up the equation regardless. Okay. And so this is actually another good example here of a non-standard cash flow conversion. I was actually going to do one like this at the beginning of class, but then I remembered that we had an example like this later, and so I wanted to wait until now. And so this is a good example of how you convert a non-standard single sum into a series that spans the whole thing. All right, and so hopefully this will give you a good picture of it, because we're doing everything in terms of symbols here, and so you can see the entire equation kind of span out. Okay, and remember this EUAW. This is an EUAW for the entire 10-year lifespan. Okay? And so everything has to be converted here to a uniform series that spans that 10 years. Okay, so let's start with the first initial purchase. And so the initial purchase, we have a minus P sub A. Okay. Thankfully, this one here is standard, and so we don't have to do anything special for this one, because this is a present sum on year 0, which is the standard form for present sums. And so to convert this to a uniform series, we just have to do one conversion. And so it'll be A over P, 8%, and 10 years. Okay. And so that's going to spread that single uniform series across the entire way. All right. Let me do the other standard one here, and then we'll do the non-standard one, just so it's kind of more highlighted. And so the other one that's actually standard here is going to be F3A, because that's a future sum that happens at the very, very end. Okay, and so that's a future sum that's on year 10, and so we can spread this out over the 10 years prior with a A over F conversion. Right, so it's going to be F3A, A over F, 8%, and 10. Okay. So that's a standard future sum to uniform series conversion, because the future sum is occurring at the same time, at the same end time as the uniform series. So now let's do this. And so this right here, this is a future sum, these two together, but it's not in year 10, it's occurring in year 7, right? And so to convert this to a uniform series that spans the entire 10 years, we have to do this in 2 steps. Okay? But we can kind of follow the same process that we did before. And so first thing we want to do, first let me write up the value for this. And so since this F sub A and this P sub A are occurring at the same time period, we can actually add their values together, or in this case, subtract them, because they're happening at the same time. So it kind of saves us a little bit of work. Let's try to do F sub A minus P sub A. Okay. Right, because that's kind of the total amount of cash flows occurring in year 7. And then let's convert. And so first thing I'm going to do is I'm going to take this future sum and then take it all the way back to year 0. Okay. Right, so we have a P over F, 8%, and we're taking this back in time 7 years, and so our end value there is 7. So with this conversion, this takes this future sum back to year 0. Okay. So present day is actually a good place to be, because usually from present day you can go anywhere that you want. Okay. Because we've already done a conversion between present day and a uniform series over this 10 years, and that was this one right here. Right? So let's apply that same conversion. And so if we multiply this by A over P, 8% and 10, okay. And so this converts P to A. Okay, let's convert the P to an A over those 10 years. Then that's exactly what we want. Okay? So now all 3 of these cash flows are in the same form. They're all in uniform series form. And we can go ahead and compute this. And so of course, we can't fully compute this because we don't know the values of PA, FA, or F3A, but we can at least look up the values in the table. And so if we look up these values in the table, what we get is EUAW of A is equal to minus 0.236 PA, okay, P uppercase A. Okay. Then we have plus 0.087 F sub A plus 0.069 F. And so once you know the values of the initial costs, the salvage value, and the early salvage value, you just plug it into this equation and you get your answer. All right. Any questions on that? Okay. All right. So let's do option B, and let's do it relatively quickly. All right. Machine B, remember, has a useful life of 13 years. And so we're actually never going to salvage this at its end of life. And so if we draw its cash flow diagram, it's actually very straightforward. And so for machine B, we have its initial cost, which was P sub B, which we don't know. And then finally, we have the salvage value. And so the salvage value for a machine B, we're only given the end of life salvage value. And so even if we use it for the 10 years, this here is technically an early salvage value. And so we'll call this F10B, because we're salvaging machine B after 10 years of use. All right, so let's go ahead and compute the EUAW. And so we have minus PB times A over P, 8% and 10. Okay. Since the PB there is the standard form for a present sum, we can do this in one conversion. And it just so happens that the F10B here is also in standard form. And so we also only have to do this one step. And so it's F10B. We're going to convert it A over F, 8%, and 10 years. Okay. All right, and so we look up the values in the table, and what we get is minus 0.149 PB plus 0.069 F10B. right? And so, of course, we can't come up with a conclusion for this one because we don't, it's all going to depend on the values of the initial costs and the salvage values, but at least we set up the equations, right? And so the idea here is that once we know these values, we plug them into these equations, we see which one's higher between A and B, and then we choose that option for this project. All right, any questions on this? All right. And so that's kind of most of the nuance that's associated with annual cash flow, right? So we've been doing kind of economic comparisons for 2 weeks now. The last thing I want to go over from this that kind of goes along the same lines is something known as an amortization schedule. And so this is kind of a good way to kind of break down, loan repayments. Okay. Okay. All right, so kind of going along this lines of annual cash flow analysis and uniform series, I think one of the most common applications for this, for businesses, for engineering firms, and just for people in general, is to, figure out how to pay back the loan. Because a big part of taking out a loan is that you have to pay, of course, you pay back the loan, but a lot of what you pay back actually is not just the original amount that you borrowed, it's also the interest that you're paying on the loan as well. Okay. And so what can be useful sometimes is to kind of break down a loan repayment kind of period by period, month by month, to see, how much of your payment is actually going towards paying off your debt versus how much is going off to paying off the principal. Okay. Because the way it works is that, say you borrow some money, and so you get a large amount of money, P, okay? And then part of the arrangement is that with your lender, is that you agree to pay a fixed amount of money each month or each year, repay that loan. Okay? And so we'll call that amount A. And this A, a certain percentage of that A is going to go towards actually paying off the principal, while a certain amount of that A is going to go towards paying off the interest. Okay. Because basically, the way a lot of these loans work is that the bank is going to charge you extra money to use their money, right? And so each month, when you have to repay a loan, the bank is going to say, you owe this much on your loan left. We're going to take a certain percentage of that, and that's going to be your interest payments for that loan. Okay. And this ratio, the ratio between principal and interest, will evolve kind of as you make more payments. And so a good way to keep track of this is to build what's called an amortization schedule. And so the last topic will be how to build this amortization schedule. Okay. All right, so these are really useful. And actually, I built a lot of these myself, over this past year. Because my wife and I, we were in the market for a house for a while. And so it was really useful to know, how much of our mortgage payments would actually go towards paying off the house versus going to the bank. And it's good for checking too, because if we're on Redfin so much, and you see the estimates for how much your monthly cost would be. It's good to kind of just double check those numbers just to make sure that they're right. Because something like a house or a car, these are really big decisions, and so you kind of want to really dot all your I's and cross all your T's. Do the calculations 3, 4, 5 different times just to make sure that the payments are what you expect them to be. All right, so here's kind of the anatomy of an amortization schedule, right? And so there's kind of a top portion. And so the first thing you're going to write down for an amortization schedule is what the initial balance is. And so that's usually how much money you're going to borrow. Okay. Next thing you're going to write down is the interest rates. Okay. Then you're going to write down the number of payments. And then you're going to write down the payment amount. Okay, so that's how much money you're going to pay each month or each year to pay off this money. Okay. All right, so that's kind of the header portion. And then now comes the table. And so this is kind of where things kind of really start to break down. All right, so the first column you're going to make is for the period. Okay. And so each pay period, you're going to give it a different row table. And so for this example, let's say we have 6 pay periods, and so I have 6 rows here. The next column you're going to have is one called beginning balance. And so that's how much of the loan that you have yet to repay. Okay. And so that's the beginning balance of that pay period. Then you're going to compute the interest, or how much think of this as kind of like the fees, or the fees that you pay for that period. Then once the interest is paid, then you can see how much of the money that you have left from your payment that's actually going towards paying off your loan. Okay, so that's what we call the principal paid. Then once you know how much of your loan that you're paying back that period, then you can compute how much money that you owe left on the loan. So that's called the ending balance. Okay. Okay. And so that's kind of how it looks like. And so, this kind of forms very naturally into kind of like a spreadsheet. And so a lot of people build these in spreadsheets. And so they write all the formulas in the spreadsheet, cells. They kind of do that. But, for now, I'll show you kind of how to break this down just using hand calculations. So you understand everything that's kind of going on. Okay. And so let's go ahead and fill in, what these values are. So the initial balance, that's often your P, or the present sum of money that you're taking out for the loan. Okay. Your interest rate is I. Okay, so same symbol that we use for interest rate this whole time. Your number of payments, that's going to be the number of time periods in your economic analysis, and so that's N. And then finally, your payment amount. Your payment amount is a uniform series kind of conversion of your initial balance. And so we have A, which is equal to P A over P, interest rate, and N. Okay. Right. And so that's the only part there, your payment amount, that you have to use either the compound interest tables, or I think what's more common, in practice, because oftentimes, you're going to get an interest rate that's not, perfect 3%, 4%, 5%. It's going to be somewhere in between, like 3.2, 3.7%. You might have to use a formula to perform that cash flow conversion. Okay. So let's go ahead and break down, how we compute each column. Okay. So again, it's the beginning balance. This is how much money is left on that you have to pay back at the beginning of the pay period. Okay. And so the way you obtain this is that for period 1, and so for the very first row in the table, you're going to set this to be equal to the initial balance. Okay. And so in the first row here, you're always going to have a P right there. Okay. Okay. And for all other periods, you're going to set the beginning balance equal to the ending balance of the previous period. Okay? And so let's say at the end of year 1, we end up with an ending balance of, we'll call it P2. Okay? Right, so that's after we subtract the principal paid to compute the interest. Okay. And so the beginning balance for period 2 is going to be P2. Okay. And so whatever we ended with at one time period, we're going to start with at the next one. Okay. All right, so the interest, this column shows how much interest money you owe your lender for that time period. And so each pay period, you're going to owe a certain amount of interest, and that column there is going to track how much interest that you owe. Okay? And so the way to compute interest is that it's just a percentage of your beginning balance, and that percentage is the interest rate. And so the way you compute it is you take your interest rate and you multiply it by the beginning balance. And so interest is equal to beginning balance multiplied by I. Where of course, you're gonna express I as a decimal instead of a percentage. All right, next we have the principal paid. And so this column here is going to show how much of your payment is actually going towards reducing your balance. And so the way that you compute this is you take your payment amount, which is A. Okay? Remember, we computed A using that that cash flow conversion there. And then from that, we're going to subtract the interest. Okay? Not the interest rate, but the interest payment that you computed in the previous column. Okay? Okay. And then finally, we have the ending balance. And so the ending balance is the amount left on the loan after that period. So after you paid off some of the interest, after you've paid off some of the principal, your ending balance is how much you have left. Okay. And so the way to compute that is to take your beginning balance. You take your beginning balance. And then from that, you're going to subtract the principal paid. Okay. Right. And so that's how you do all the columns. And so basically the way you build the schedule is you do it kind of row by row. And so you start with the first row, you compute the interest, you compute the principal paid, the ending balance, you move that ending balance to the beginning balance of the next period, and then you just kind of repeat this calculation kind of over and over. And so, I will admit that when you do it by hand, it is a little bit tedious. It's kind of just a lot of numbers you have to punch into a calculator. It's not particularly difficult calculations. It's just, just kind of annoying to do. And so for this reason, for most people, we typically do these in spreadsheets because, Excel or Google Sheets, they can automate this process for you. But it's good to kind of work at least a couple of these out by hand, just so you know kind of what's. Okay. All right, any questions on that? Oh, yeah. Sorry, I know I do that a lot. So I scroll up to look at something and then I forgot that people are still writing something down at the bottom. All right, so we have 4 minutes left, so I don't think I have time to do the example, and so we'll do that first thing on Tuesday, if I'm alive on Tuesday. But I do want to kind of tell you some general trends that you can kind of expect from it. And so, generally speaking, when you're kind of early on in the loan, what you'll see is that your interest payments are quite high. They start high because, if you look at how interest is computed based on how much beginning balance you have. So the more balance that you have, the more interest payments that you're making. And so if your interest payments are high, then your principal paid is going to start low, right? Because your principal paid is just kind of just whatever's left over after the interest is paid off. But kind of as you progress, as you make more and more payments, the relative amounts of these two are going to be flipped. So kind of as you get towards the end of the loan, the interest payments will get lower and lower because the balance that you have left is going to be lower and lower. And then as you progress further and further, a larger chunk of your payments are actually going to go towards your principal. Okay, so these are going to be much higher. Okay. And so, I think for most people, when you first look at a table like this, it can be really discouraging because, you're making these payments, right? You're making these payments here, but very little of that is actually going towards paying off your debt. So a lot of it's actually just going towards paying off the interest. And so you kind of have to, make a few payments before things kind of really start going. And you can say that, you owe the bank a little bit less money. And this gets even more extreme when you look at even, larger purchases. And so if you purchase a car, or you purchase like a home, right? And so these are payments made monthly over several years of time. The traditional mortgage for, buying a house is 30 years. And so you take 30 years multiplied by 12 months, that's like 360 payments. And so, I think a lot of, when you kind of first do the calculations, I know my wife and I were surprised that, out of the payments that we were making, initially about 99% of it is actually going to go towards the interest early on. And only about 1% of it goes towards actually paying off the principal. Right? And so it kind of felt like, we finally got out of renting only to pay a different landlord. So now our landlord is Wells Fargo instead of, the landlord of our apartment. But, as over time, as we make more payments, that those ratios start to drop. And so, and you'll see that in the example. So when we come back on Tuesday, we're going to do an example of this where, these trends, you'll kind of see them in real time. So you have a better idea of how these loans are structured. All right, any final questions before we wrap it up for today? Okay, all right, and so that's all we got for today. So hope everyone has a good weekend. Thank you guys for coming today, and have a good rest of your day. And I'll see you next Tuesday. And oh, by the way, if you turned in homework 1 in paper, I have it here. I finally brought it, and so you can come pick it up here at the podium. There you go. Write your name next time.
Bye-bye.
Sure.
I was thinking kind of individually.
Yeah, that works. You can do that.
Yeah, but then the very
Sometimes, because these conversion factors in the table, especially, they cut off the decimal at the 4. But they actually work. So if it's just a little bit off, like 1-2%, it's fine. If it's really wrong, it'll be a lot. Yeah, especially if you use a different approach than I did, or if you use the equations, you're always going to be a little bit off.
and another question for the next one.
Yeah.
Also, first.
Mhm.
It can be language problem too, and it can be a problem. But when I looked at it, there was like initial $1,000 from the parent.
Yep.
And then 1,500 from I think some parents, and then it should be more upward than 1,500. That's to pay back the 12 tuitions.
Yep.
Yeah, and then it should be in uniform series.
It should be a gradient for that. So what's happening is that from here, the parents are going to be contributing more and more each year to compensate for that. So and so what you're computing here is actually
Not the uniform series.
Yeah.
I was doing kind of confusing with the non-compound, non-compound cash flow. I don't really know with this. And you think there's this equation kind of similar as the answer.
Let's get P is equal to 1,000 minus 20%. Yeah, right. Yeah. And so this one also has to be a non-standard one too. So, you can kind of use the same idea. You convert it to kind of a single sum. And so if you convert to a single sum, you put it, if the gradient starts here, and if you convert to a single sum, you're on your 7. The gradient will start 2 years after the finish one.
Yes.
And then you convert that back to P E over G. Right. Yeah, 7, 7, 2, however much it is, 7, 2, 17. And then go Q over F from year 7 to 13.
72.
Yeah.
Analyzing loans.
Oh, I can solve this. Is it this one right here?
Yeah, the thing on the. Box.
And then there's a,
Yes.
an orange.
Yeah, so those decimals there, those are just the percentage, those are just the
I
decimals. you
remember
get
being
from
the first time.
Yes. Yeah. So I'm reading basically, these are my lecture notes, and so I post a lecture. You can look at those.
On the homework, just like for first problem, there's like the question that is particularly in the first two periods of the gradient cash flow. It said like, explain why there's no cash flow in the first two periods.
Yeah.
So other examples besides like maintenance costs, or did I just say that?
So it's kind of more based on what the gradient represents. The gradient represents the increase over time. And so in the increase, what we kind of assume is that year 1, year 0 is present. Maybe no cash, unless it's a present sum, there should be nothing on year 0. Year 1, you kind of consider that as like the baseline for any kind of recurring. And then any increases are going to occur after year.
Which is why it's standard, because the first 0 and 1 was just the starting, regarding whatever the.
Exactly. Okay. Yes. Mhm.
Where is it?
So is there any final questions from Zoom? All right, I'm up with that. All right, see you guys next week. See you guys.